Hello, this video is going to be about closed loop zeros. There's a lot of talk about placing poles and such, but I want to go into a little bit more depth about zeros. So to start with, I'm going to define my open loop system. I have a gain, a corner frequency, and this would be for a simple motor control velocity mode. By adding an S in the denominator, I'm integrating the velocity into a position. This is the PID in Laplace transform mode or transform mode. And this is the definition, basic definition for a closed loop transfer function. So if I do the substitutions, I end up with this. And if I simplify this equation, I end up with a numerator and a denominator. The denominator is called the characteristic equation. That usually determines whether or not you're going to overshoot or oscillate, or how the system's going to vibrate. The numerator, it has the zeros. So if you have the roots of this, that's the zeros. If you have the roots of the denominator, that's the poles. The next step is to calculate the pole locations, or to compute where the pole location is going to be. And I'm going to set them at minus lambda. So I have, since there's 3 poles here, I'm going to have 3 poles in my desired characteristic equation. I end up with this equation, and I match the coefficients for each power of s, except for I don't have to match those. So I end up with this, and then I can solve and I get the symbolic equations for the PID gains. Then I'm going to define some values. So my open loop gain is going to be 10 millimeters per second per percent, and my corner frequency is going to be 10 hertz. If I multiply it by 2 pi, I get it in radians. And then if I invert that, I get the open loop time constant. I'm going to want to put the 3 poles at minus alpha, or at the same location. So the poles are going to be at minus lambda, and the poles are going to be at minus alpha. So with that, I can calculate out my PID gains as a function of the open loop gain, the bandwidth, and the location of the 3 closed loop poles. I can also calculate out the feed forwards, but I'm not using them right now. This is for simulation. This is how you set up the equations or the matrices for in continuous time mode, and then you have to convert it to discrete time mode for doing iterations. My state variable x has the actual position and velocity. This would be what you call the process variable and the derivative of the process variable. This is my PID controller. This is the basic equation for updating the state. Here I'm updating the control output, U, but this is the P and the D terms. So I have the P and the D gains, and that's multiplied by the target position minus the actual position, and the same thing goes with the velocity. These are um, vectors. So there's a position and velocity in each one of these. This is the equation for the integrator term. So what I got to do is return the new position, x1, and I have to return the total control output, and then the integrator term has to be done separately because I'm keeping track of the integrator term separately. I'm making simple step jumps in position, and I like to do that to see how the system responds. So you can see the control output does make a jump to 100, and you can see though that the actual position goes nicely to 100, and then it goes down to minus 100, and then back up to a minus 50. There's no overshoot, and that's all by design. This is the same thing showing the velocities. The velocities are going almost 1,000 millimeters per second, and that's about the limit. Now, if I just want to do a normal point-to-point move. I can use cosine ramps. So I'm ramping up, going at a constant velocity and ramping down. I'm going from 0 to 500 millimeters, and I'm doing that in 1 second. I'm spending about 1/3 of my time ramping up, 1/3 of my time at constant velocity, and 1/3 of my time ramping down. And the frequency of acceleration is computed by taking this time, which is 0.333 seconds. This is another third of a second. You add the two together, get 2/3 of a second, invert that, and you get the frequency of acceleration, which is 1.5 hertz. But the controller has got a bandwidth. The controller and the system have a bandwidth that's greater than 1.5 by a large margin. So it tracks fairly well, even though there's no feed forwards. There's a little bit of error in here, and you can see the error show up a little bit more when I'm plotting the velocities. So let's look at the Bodhi plot. Again, this is my closed loop transfer function, and I'm going to show the Bodhi plot. And it looks pretty good, uh, but what is disturbing is this one little section right here where the gain goes up above 1, and that's not desirable. But the PID has, or this closed loop transfer function has a bandwidth of almost 25. And I did that by just kind of searching along this line here till I get to minus 3 dB down. So if I plot this out, my poles are at minus, this is 2 times pi times 10, and I got three poles on the negative real axis here. They're all at the same location, even though it looks like only one pole. And then there's 2 zeros, and one is at the same location as the poles, and the other one's at 5 times 2 times pi, which is here. And you can tell if the system's going to have a gain greater than 1 by the location of the 0 relative to the poles. Because if you scan this way and you get to the zeros significantly before you get to the poles, then you know that the gain is going to increase because the zeros tend to add energy to the system before the poles will start to have it decay or absorb the energy. So if I take the closed loop transfer function and I have a step jump, this R over S is step jump to 100 millimeters, and I do the substitutions for these gains. This is the transfer function as a function of, or the response as a function of time. And you can see the e to the minus lambda, that's due to the 3 poles at minus lambda. Now, I can do the same thing for a pi minus d. Now, notice that there are 3 gains and they're in the numerator. That means that they're in the forward path. They're acting on the error between the target and actual position or the set point in the process variable. In this case, this is a case you see in many PID controllers on PLCs, and the PI is working on the error between the target and the actual or the set point in the process variable, and the D is only acting on the rate of change in the process variable, or in my case, the rate of change or the error in velocity, which is the rate of change in position. Now, the difference between them in the Laplace transform is that I don't have this D term in the numerator. So that means that there would be a D term only in the feedback path. Now I can have an I minus PD. This form of PID is overlooked significantly, and you can see that I've got only a KI. There's no P in the forward path. So this is going to have a slower response yet, but this again is the transfer function, or the response is a function of time. And so I have the 3 responses as a function of time, and I can plot them out. And notice that the PID response is here, and it's a little bit faster, and it doesn't overshoot near as much as the PI minus D. And it's amazing that they use this in PLCs because it's not as good as using either the normal PID or the I minus PD. Now notice that the I minus PD is slower to get to the set point, but basically it converges at about the same time, and that's because the three poles are going to always decay at the same rate, no matter where the zeros happen to be. The zeros are causing this overshoot here. The I minus PD has no zeros. So let's look at this is a repeat, and we're going to look at the closed loop transfer function again. And you can see again, there's this little area where the gain is greater than 1, which is not desirable, but the bandwidth is high. And then if I do an I minus PD, I remove the D term up in the numerator, but I have to keep it in the denominator because this is the feedback path. And if I plot that out, it looks about the same as up here. But I want you to notice that this is a plus 10 and this is minus 10 on this scale. And then down here, this is plus 20 and minus 20. So this error is actually about twice as big, which is what you saw in the overshoot up above when you're looking at the responses. Notice that the bandwidth has also decreased quite a bit, and that's because you have one less zero to add phase and gain. Then on the I minus PD, again, there's no proportional term or derivative term in the forward path, but they're still in the feedback path. And there's going to be no overshoot. There's going to be no sections where the gain is greater than, well, here we have 0 dB or 1. And the reason why is because there's no zeros. But the penalty you pay is to get a lower bandwidth. So let's just plot these out so you can see what it looks like. If you're just going to do step jumps, again, as seen above, the convergence is going to be about the same unless you add the zeros. And then I showed you the integrator trick. Now, if I use the cosine ramps on the I minus PD, whereas above there was hardly any error between the target and actual position, here you can see there's a significant phase delay between the target and actual position. So, in short, the PID gains will add 2 zeros. They will extend the bandwidth and it'll give you a faster response. But unless you happen to have a correction for the integrator winding up, you will have overshoot whenever you have a step jump or you're just trying to do a simple point-to-point move. If you want to avoid that, you can use a I minus PD control, but then you're going to have phase lag. So the trade-off is bandwidth for overshoot. That's it.